For chapter 3, we'll be getting into inverse functions, but first let's go over the exponential functions. So f of x equals 2 to the x power. Pretty simple there. X is an exponent there, that's why it's called an exponential function. In general, f of x is equal to a of x, where a is positive, but it doesn't necessarily have to be, because there can be a coefficient of -1 up front. So yeah, a of n, so a of any number is just going to be that number multiplied n amount of times. So let's just say n times, such that 2 of 4 is equal to 2 times 2 times 2 times 2. So the base multiplied by itself n times, which will be 4 in this case, which is 16. That's some logical things here. Assuming that a is not equal to 0, f of 0 is always equal to 1 for exponential functions, because a of 0 is always equal to 1. Pretty simple there. So here's my question: how do you evaluate irrational integers? So yeah, actually, irrational integers is a contradiction in itself. Irrational numbers. Oh, I just clicked it again. Let's say a over pi. Well, you're gonna say, okay, that's a equals 3.14159.265, so on and so forth. So you're gonna go a times a. That's 2 times a times a. What do we do for the last one? Well, logically speaking, it would just be 0.14159, and so on and so forth. Obviously, because I know my exponent rules. So that's the logic there. But here's the thing: this goes on forever. As we know, pi is irrational, which means that it can't be expressed as a fraction. Which is funny because pi is the ratio of the circle's circumference to its diameter, which means that it's a fraction, I guess, in itself. But again, the circumference is perfectly circular, so that's why it happens as a case of that. So then we have to use limits, and that's where the calculus comes in. So it's going to be the limit as x approaches pi, for a of pi, or for a of x, is going to be equal to a pi, or not a pi, theoretically, but it's going to be approaching a pi, which is what we define a to the power of pi is. So for example, let's say that a is equal to 2, then the limit as x approaches 2 is going to be a of, not 2, a of x. It's going to be, or sorry, it's actually wrong. I meant limit as x approaches pi of a of x is going to be, or sorry, that should be 2. I keep messing up. Okay, pi is going to be 2 of pi, which is going to be probably, limit you can just go really close, so it'd be 3.14 maybe. You can even get more precise, 2 to the power 3.141, so on and so forth, and the limit should be equal on both sides because exponential function is continuous. So that's how you approximate it, such that 2 of pi is equal to somewhere roughly around 2.3.14 and probably to 3.15. So you just get closer and closer, which makes it more precise. Again, precise definition of limit. So yeah, the logic there is pretty sound. I forgot to mention that if x is rational, then you can rewrite, so if a is equal to x, or actually let's use a different number, let's use z, then you can rewrite, and if z is equal to p over q, then you can rewrite this as a is equal to p over q, which is the same thing as the a to the power of p to the 1 over q, which is the same thing as a to the p and to the q root. So like if you're ever confused on what 2 to the power of 1.5 means, it's quite simple. It's just 2 cubed square root, which is going to be square root of 8, which is probably some number. I think it's, I don't know actually, so I won't say. So there's 3 kinds of exponential functions. There's functions where a of x, for example, a is positive, or they say greater than 0, which is the same exact thing. But before we do so, we'll go over the positive cases where a is greater than 0 but less than 1. So then the limit, or actually let's draw what the function will look like. Generally, it'll look like this. Well, obviously the base will change things a little bit, depending on if it's 0.5, 0.7, but generally it will look something like this. Let's use some logic here. A negative. So if one, let's just say it's 0.5x, or yeah, let's just say that it's 0.5 to the power of x. Remember that x is pretty negative, so it can be 0.5 negative 4, which is the same thing as 1/2 to the fourth power, which is going to be 16. So it gets increasingly big as x becomes more negative. So that's the first case. So a to the x, when a is equal to 1, no matter what x is, 1 times 1 times 1 is always just going to be equal to 1. So this always looks the same regardless. So you'll never actually really use this. I guess. I mean, it'd be practically useless. It's constant. And if a is greater than 1, the exponential function looks like this. A of x. Quite simple. Properties of exponents. If a is greater than 0, and a isn't equal to 1, the f of x is equal to a of x is equal to a continuous function. So, if a is going to be equal to, I'll use like kind of set theory. X is greater, 0 to -1 interval, or 0 to, or not even 0, doesn't include 0 actually. So greater than 0, or greater than 0 excluding 1, then it's a continuous function. So depending on what x is, or depending on a, it should be a actually. I just use x as an input variable. But if a is greater than 0 and not equal to 1, then it's continuous, which is pretty illogical. The reason why it doesn't work for negatives is because theoretically it would be undefined for certain values. So yeah, just exponent rules. This should be, you should learn this in like algebra 2, but I guess we're still learning it now. Ay is equal to ax plus y. Ax divided by ay is equal to x minus y. I think those are the really only two you need to. Oh, actually no, there's a few more. A x y is equal to a y x, so just product, and then a b to the power of y is equal to a y b y. So yeah, simple logic there. Limits, just understanding the limits, general limits of each one. Lim as x approaches infinity of a of x is infinity if x is greater, or if a is greater than 1, because any number multiplied by itself that is greater than 1 will always give you an astronomically large number, which is where you hear the term exponential growth actually. It should be x equal to 0, simply because you flip the fraction, because if x is greater than, I guess you can make it a piecewise function, but I won't do so. So yeah, that's the logic there. Just understand that. Pretty simple stuff. And likewise, limit as x approaches infinity of a of x goes to 0, and the limit as x approaches negative infinity of a of x is equal to infinity if x is less than 1 and greater than 0. Logic there. I don't even know why we go over the natural logarithm, which is just a special case where it's e to the power of x, the natural exponential function. But Euler's equals limit as x approaches infinity of 1 over x over to the x power, which you learn about this like for finance. So yeah, yeah, it's basically all that is for 3.1. So yeah.